Okay, so here my notes are not super good for this density of state, just figure is correct and final formula. But, okay, so we see that there are quasi-particles, and depending on the K, as I was explaining, when K is far away from the Fermi sea, it looks like electron, and if K is far below the Fermi sea, it really looks like the true hole, or which means like really missing electron. And close to the Fermi energy, then it's like a superposition. The excitation is actually the superposition of the hole and electron. It's something like that, 1/2 hole and 1/2 electron, right? Because U and K are roughly 1/2. So then you see that quasi-particles are strange object. It's a mixture of electron and hole, okay? So they have actually zero charge because you have a contribution from U and you have contribution from V. So you have electron charge, hole charge, one is plus, one is minus. So the charge of the quasi-particles, if you look for the charge of the quasi-particle, then the charge of the quasi-particle is UK square minus VK square. This is the charge of the quasi-particle. Because this is the probability that it's the electron, and this is the probability that it's a hole. You just look for the picture UK and VK. Yeah? So basically exactly when UK and VK are 1/2, which happens exactly on the Fermi energy, then the quasi-particles are effectively chargeless objects. Okay? Good, so that's what I'm just saying. So the other thing, and this is useful when people really do some calculation in the superconductors, you can also would like to do the same things and use the trick that if you're in the superconductors, you also want to use the trick that summation over K, you change to the integration over the energy, but you should be a little bit careful because now the energy is not just the parabolic, but a little bit complicated. So the point is to calculate the density of states. And I will just show it how to calculate it. I will not make the full calculation. This maybe is the good homework problem, but I will just show you the things, why it's done and how the picture looks like. So again, the story is like that we compute some superconducting properties. And this typically means that you are having some summation over K, and then you are having something, and there is like the distribution function which depends on the energy of the quasi-particles, and there is some other function, I don't know, G, which depends on the energy of the quasi-particles. And again, as before, we can make the continuous summation, and we want to change it to the density integration. So first of all, if I am making the continuous approximation, then this will be V divided by 2p divided by 3, and you can change the summation to the integral. But since the things are just depending on the energy, so the final function here is just depending on the energy, not on the actual momentum, then there is the last other trick, and we change this to the integral over the energy, and what we need is the density of states. Okay, I will call it E, and then we are integrating over the energy. So we need to know these things. Yeah, this is the things which helps the things to, okay. And the density of state is always calculated in the same way. It is the volume divided by 2p to the power of 3 in VR in 3 dimensions. And then you need to make the integral d3k in 3 dimensions, and then you put the delta function, and you take the energy minus energy at given k. So this is the things which you need to calculate. Okay, and our EK is already what was written, right? EK is given here. Okay. So this I can already start to approximate with the density of states of the normal things. So this I can write it, it is, what I can do is, it is 2p divided by 3. Or what I can do it, this integral, I can already write this integral as the integral over psi, density of states in the normal state, I will call it n psi or n0 or n psi, and then I can write this is the delta function, and this is E minus, and the energy EK is xi square plus delta square, which I can just write directly like this. I'm using the things that integral over the momentum, I can write as the integral over the energy, and I'm using now the non-superconducting energy for that. Okay? And the main trick is that if you're integrating over the delta function, you should remember the following trick, that if you have a delta function of the function which depends on the psi, then this is nothing else as a 1 over the absolute value of the derivative of that function at point f psi 0 equal to 0. So you need to evaluate it at that point, and then that's just the delta function over psi. Right? This is the main property of the delta functions. Right? So these things I need to do. Now this is my function f of the psi. So I need to make this trick if I want to calculate the things. And I'm just showing you the final result. So at some point I need to calculate this derivative, or precisely opposite derivative. But this opposite derivative will be here. So in the denominator, I will have the derivative of this function with respect to xi, which means if I'm changing about, I have a derivative of xi with respect to e. Okay? Do you get what I'm saying? So the final answer is like that the density of states looks like here, and this is the final result. So it's obvious. When my energy is smaller than the gap, I don't have any quasi-particles there. My excitation spectrum has a gap. I don't have particles between 0 and delta. So I cannot have a density of states. If my energy starts to be larger than delta, I'm having a density of states, and you see this formula. So close to the gap, figure is here. So you see that if my energy starts to be here, around these things, you see that I have a very large number of quasi-particles existing. Okay? This thing is called the coherence peak, and people are able to measure it. So the typical experimental measurement which is done is that there are measurements which are able to measure the density of states. And the people are doing the STM spectroscopy. So they take the sample, they put on top a tip, and they start to tunnel the electron from the tip to the sample. And they are able to measure how much energy you need, or they are applying a voltage actually between the sample, how much energy you need to put the electron inside of the sample. So if the energy is not enough, the electron cannot go because you are putting electron has the energy smaller than delta, so he cannot go because there is not a state he can go. So you need to give the electron enough energy that he can tunnel. Electron is he, so I just saying he. Okay, hole is she. No. So then you will see that in the tunneling spectra, you will typically see what happens, and this is like, maybe I can put it to the notes, that you will see that in tunneling experiments, the people are seeing the things that they are changing the electron energy, they are changing the voltage, then they are seeing there is nothing, and suddenly, if the electron voltage starts to be comparable with the delta, they suddenly see that there is a large peak, and they are seeing such beautiful things. So what they are seeing is basically those things, but because of the final temperature effect and finite lifetimes and other interaction, which I don't have into the system, I just consider a system that, there are also other interaction in the system. Electrons are having finite lifetime, there are impurities, so these peaks are not going really to infinity, but they are a little bit rounded at the end. So you need to make some phenomenology, you will need to do some smearing. So this is zero temperature results. In the non-zero temperature results, you are having also some smearing of that, and this is typical things which you can see. Okay, so this is then 2 delta, this is this gap, and you can measure this height, and this is this coherence peak, people see. And this is the proof of the superconductivity, normally, okay? And most exciting is if you see something extra, that you see that inside there exists some gaps, some subgap states, and then you can have some delta function contribution there. And this is interesting because you discover some subgap states in the superconductor. One example are the U-Shiba-Rusinov states, or Majoranas are a very particular case, and they are having a zero energy Okay, but this means we need some other theory to get that. Okay, yes, David.
Why do like rise to very high and then decrease? That's for the validity. I think for that, what?
Because dI/dV is scaling as a density of state. So the main thing in the experiment is that they are using a dI/dV curve. And from the theory, dI/dV is proportional to the density of states on the energy EV. And you are seeing that the density of states as a function of energy is very high here. So that's why it's so large. Okay? Good. So this is the density of states, and you can just really calculate this integral, go over that. I will maybe put it as a homework problem, and you will get it. Okay, also the other thing is, once you are having energy dispersion, you can start to ask about the group velocity of the given particle. Right, so group velocity is given by the derivative of the energy with respect to the momentum. And this you will get, just check it for yourself. And now you see what is the group velocity of this particle. And this is also a reason why we call electrons and holes the holes. This is the ksika, not the absolute value of ksika. So for K smaller than Fermi energy, this is a negative. So if I take a K which is smaller than Fermi energy, then I am saying that the group velocity is negative. So it's something which is moving in the opposite direction as the momentum, which is a hole. If K is larger than Fermi energy, then it's moving with a vector K. So you clearly see that there is this factor plus or minus, and it's whether it's moving along the K or anti-along the K. Okay, anti-parallel to the K. Then one is hole and the other is the electron. That's also the thing. And you clearly see also the dispersion from here, right? The gradient here is in this direction, so the group velocity is here. Gradient in this direction is there, so the velocity is there. Okay? So we see that particles here are behaving like a hole because they are having negative group velocity, or negative in sense that for positive K, they are having negative, and this like this. Okay, Doc? Good. And now I'm coming to the last thing which I want to just finish today. And this is the entropy and the heat capacity. So I just want to show you this jump. Okay, you remember when I was showing you at the beginning the experimental data, just let me refresh you. And then we go over the calculation. Okay, so the experimental measurements are showing you the following picture, that if you measure the heat capacity as a function of the temperature, T, and this is the heat capacity, then at critical temperature, you see the following things. So about critical temperature, the heat capacity is going roughly like that, and then the critical temperature you have a jump, and then it's going somehow, and then here it's going exponentially to the zero. So this is exponential, and here is a jump, okay? And this we're gonna to derive. And you will see that BCS theory has the answer for that. Okay, so let's make the calculation. So again, just remind you, the heat capacity C, which I'm gonna to calculate, is T time, and this is a derivative of the entropy with respect to the temperature at fixed magnetic field, or everything else is fixed volume, magnetic field, everything else. So we need to calculate this derivative effectively. Okay? So the formula for the entropy, if you know the occupation numbers, and if you had the course of the statistical physics, this we derived there. So this is the formula for the entropy. Once you know the occupation numbers, which is these Fermi distributions, you just basically use this formula. Okay, then you need to believe me, or you had it, someone derived for you, but this is how the entropy looks like. And in that case, I'm writing sigma, but this sigma is 1 and 2 because our quasi-particles, they are having index 1 and 2. Okay, But 1 and 2 is actually the spin, but I'm not talking about that, so we are having, so sigma is that. So I need to calculate this thing, so I need to calculate this thing, so I need to calculate the derivative of this guy with respect to the temperature. I just need to calculate the derivative of the entropy with respect to the temperature. And the thing is, like that instead of doing the derivative with respect to temperature, I will firstly differentiate with respect to F, and then F with respect to temperature. And it's like a composite derivative, okay? And it's pretty easy to calculate this guy. So you just take this guy, and you make the derivative of that, and you are just getting it's a logarithm F over 1 minus F. Okay, it's also super easy to calculate. And if you know the formula for F and minus F, which we know, yeah, it's provided here, and you just take the ratio of those two things, you are even getting the difference between those two things is just add to the minus EKBT. So, complete formula for the heat capacity, okay, logarithm of that, and also basically this is the formula for the heat capacity. Okay, so this is the exact formula basically, which you can get. And here, sigma, as I'm telling you, I have two types of quasi-particles, gamma 1 and gamma 2. So the sigma is for that. So energy is degenerate, so I can directly write 2 times and don't have any sigma here, okay? Okay, so now I'm just making how this, so you can numerically calculate that. Or you can use the continuum approximation, and you can change these things to the integral over the energy and things like that. So you can integrate it numerically if you want. Okay, but I just want to show you some analytical results. And okay, just remember, if you are now making the derivative of the Fermi distribution with respect to temperature, the temperature enters in 2 things. It enters explicitly here. You see the temperature is hidden here. This is the one term. But the temperature is also hidden in the energies, because energies are depending on the gap, and gap is depending on the temperature. Okay? So just keep in mind, this energy is also depending on the temperature via the gap function. And this is exactly the thing which will give us this jump. Okay? We will see. Good. So basically the rest thing is just, let's call it the mathematics. So, okay, I just define this, add to the KBT, I just define this, okay, then this Fermi-Dirac distribution just looks like that. And now if I'm making the derivative of that thing with respect to temperature, I need to firstly differentiate this as a function, you can check it just that, and now I need to differentiate this guy with respect to temperature. But I'm telling you, this guy depends on the temperature of 2 things. Temperature is hidden here, and the temperature is hidden here. So if you are making the derivative of that guy, you will get this thing. You can check it in details, but I'm just telling you how it comes out, okay? So the final, okay, let's say then it follows, then you need to calculate this thing if you add really at the moment, and now make the summation. So, exact formula so far is written here. So this thing, if you just take, is exactly like that. Okay, so I'm just writing like that. So this comes from that. Good, I'm I think repeating too much here. Okay, this energy, yeah, it's like that. So okay, I can just write it. I just written in here. Because energy is just hidden in the delta, so basically derivative of the EK with respect to temperature is nothing else than the derivative of delta with respect to, because EK depends on the temperature only via the delta. So basically you can just check that, okay, this is also the true things which I have. Good. So we got some, let's say, complicated expression. And now I will make the 2 limiting cases. So I will solve this equation for the temperature very close to 0, which means far, far away from TC. So it means somewhere here, and then around the TC. Okay? So I will do that. And we will see that if my temperature is much, much smaller than TC, that this thing is effectively some exponential. And if T is close to TC, then we will see this gap. Okay? But you see the story is like that. You use the definition, and you just manually put the things in that case. Yeah? So non-intellectual adventure here. So this is just the boring calculation in some sense. Okay, so we go with that, and I am doing the low temperature asymptotics, and in these low temperature asymptotics, just I need to start to approximate, and you remember we calculated how delta is depending on the temperature via this gap equation that is almost constant, and then it is going in this way close to Tc, this thing. So if I am at the low temperatures, in these regions the delta is roughly constant around this region. So in the low temperature the delta is equal to constant and this derivative is equal to 0. Okay? So in the low temperature this second term does not play much role. I can ignore it. Okay. And now comes the product of those two functions, f to the ek and times 1 minus f. So let's look how this function looks like, very close to the temperature, which is almost 0. And the Fermi-Dirac distribution, if the temperature is very, very small, this is the Fermi-Dirac distribution which we have. It's here. Yeah. So if the temperature is very, very, very small, then basically what matters is that this number is very, very large, so you can completely ignore this guy, right? And if I am ignoring this guy, I can bring that guy to the denominator, and it will come as a to the minus ek divided by kBt, right? I just directly write it here. That for very low temperatures, this Fermi-Dirac distribution just looks like this. Boltzmann factor in principle, okay? But now we are seeing that energies, which energies will matter? So the dominant contribution is coming from the energies which are close to 0. If EK is close to 0, or the minimum of that. If EK is very, very large, a to the minus large number divided by very, very small number is even larger number. So the exponent of minus very large number is 0, so you don't need to care. So which states are matter, I just want to say, and then 1 minus of that is roughly 1. So I just want to say that the expression is reducing to this expression that 1 minus f I can consider as a 1. Okay? So we are getting this term. Ek is equal to that, delta 0 is here, and it's a temperature independent. Okay. So the minimum states, or the states with minimum, so what contribute maximally to this sum? Because there is this exponential factor here, this exponential factor. So dominant contribution come from the K states which are having the minimum possible energy. Every other higher energy state is highly suppressed. So what are the minimum possible energies? Our excitation spectrum is here. Right, so minimum energies are the energies which are around this delta. So this is delta 0, and then I have few states which are here, which I need to take into account. So I can now make the expansion that K is almost 0, so I'm making expansion of this function, but now this coefficient is very small. This is, say, K is 0 or something around the Fermi energy. So I just make the expansion of this guy, okay? So in this case, I'm using this expansion for the energy. So energy is appearing here, I'm using this expression, and I'm using expression here. Okay? Good. So now you need to make the derivative, which is easy. And we are doing our favorite trick, that there was a summation, but anytime we see the summation, we can make the summation with the density of states. And that's like this. If you are going via energy, which is of the normal states, you are using energy of the normal states. If you go to the superconducting states, you need to use the superconducting states. But what will happen is the integration boundaries will be different. Only this I just want to tell you. So since I am having since everywhere in these formulas, I express everything via xika, I can everything express via the xika. Xika here, xika here, xika here. Since it's a xika, I am using the density of states of the normal state. I can also express everything via ika, and then I will use the superconducting density of states. Okay, what I just want to tell you is that this thing is true. If you integrate over A, with the density of states superconducting one. This is the same if you integrate over C and you use the density of states of the normal metal. And this thing is important. Okay, so I choose this one, so I'm just using this N0, and the integral over summation over K is just the integral with the density of states, which is just that. I can put there infinity, does not matter, because this exponential factor kills everything. So I can put here just infinity. Otherwise, I just need to integrate over this region. But I am say, oh, let's go even to the infinity, because the exponential factor will kill everything, okay? So the final thing is coming here. You are getting factor of 2 from the spins, with sigma 1, sigma 2. Oh, I have it here. There is first factor of 2. And then I have the integral from the energy of the normal states, which is from minus infinity to plus infinity. But it's the same as going twice just to the infinity, because I'm using the symmetry of the dispersion relation is quadratic. So, and again in this, so you see many approximations are done around here. So at the end you are getting 2 times 2 is 4, density of states, and you need to integrate this integral. Okay. Which you can take things out, and at the end you are getting some Gaussian. So only non-trivial integral is this exponent and this factor with the exponent, but this is kind of the Gaussian integral which you are able to calculate, and the result is here. So the final density of states, if you go over this calculation in this approximation in very, very low temperature, is given by this formula. Okay, some prefactor, Boltzmann constant, density of states delta to some powers. This is important powers because you can detect them. Yeah, so effectively the power of this is going as a delta to the 5½ for the BCS superconductor. So this power is important. If it's not that, then it's the traces that it's maybe non-BCS superconductivity, so people are very curious about that, but you are getting overall this exponential suppression. Okay? So this is the case in the low temperature limit. Okay, so this we derived it. Okay, it's going exponentially, so it's going like some delta 0 to the power of 5½ times a to the minus delta 0 divided by kb tc. Okay, so this is the formula how it's going. Oh, kbt, sorry, kbt. Okay. If not, today, in the machines and computer, we can calculate these integrals numerically, in principle. But you know, in the 30s or 50s, people like to make many approximations and to arrive to some simple formulas. So that's why they make, okay, let's assume that very low temperature. We need to integrate from 0 to d by shell, but because exponential factor, we can put the limit to the infinity. You know, they all make these all things, which. Okay, you can really apply close to 0. Of course, you cannot apply it somewhere here, because things are different. Okay, so now we are doing the opposite limit. Now we are doing the limit when we are going with the t close to tc. Okay, and we know with, yesterday I didn't derive it, but it's written in the notes that close to tc, the temperature dependence of the gap is given by this formula. So I was telling you that without that it's a square root, which we had before. But this is the things which you will derive if you will do it. And the derivation is given in the notes, which are some ugly integrals. So and now in the formula we need to make the derivative of that with respect to temperature, but the temperature enters only here. So the derivative is just that. So again, my formula is like this, but now I need to take into account also the second term, which is having this derivative here. Okay. Again, relation between EK and XK. But if the gap is very, very small, now we do this following approximation. So close to TC, now we do the opposite case. Close to TC, this is almost 0. So we are completely ignoring everything. So we completely put here 0 results. So everywhere here, before I have f of ek, but I'm just putting everywhere ck here. Okay? So this is the things which we are doing. So now the opposite limit. So now I firstly calculate the first term. Yeah, I have two terms here. So I'm now firstly calculating this first term, this one, right, which is this integral. Guys, as I'm telling you, this is the trick which is all the time in the solid state physicist. Summation over K go to the integration. Since everything what matters is around the Fermi energy, we are just using the density of states at the Fermi energy, so this integral is giving you this thing. And density of states, so you need to calculate this integral, okay, c squared, this, the function is like that, so you, at the end you make some change of the variables. At the end, this guy is some integral, which is many constants, and there is some dimensionless integral, which should be calculated like that. So it's the integral of this form. And those who attended statistical physics, exactly when we discussed the heat capacity of the fermion gas close to zero temperature, you already encountered this integral, and this integral can be calculated also with the terms of the zeta function, and it's the result is just this. Okay, so it's some finite integral, you can inspect it's converging, and this is the finite value. I'm just telling you that. I will not repeat all the calculation. Okay, by statistical physics we did it. So the normal state component you immediately see is giving you this result. So the first term in this formula is giving you this result, and you see it's linearly decreasing with the temperature. So it's like that. So this integral is this thing is going as a temperature, as a linearly with the temperature. So we calculated that first term is this. And now we are going to massage the second term. And the second term is this, I'm just calling it this C delta. This is like this, and this is the second term. And I now need to calculate this integral again. But this one, as I was telling you, the derivative of that with respect to temperature was easy. That was not depending on the temperature. It was just some numerical factor. And again, we get this integral now. And this integral is 1. Okay? So this expression is this constant, and integral is equal to 1. Good, and this integral which we calculated is here. So this derivative of that is really temperature independent. So this is the result which we get. Okay, so this all together. So this other constant is looking like that. So close to the critical temperature, the heat capacity in the superconducting states looks like the heat capacity of the normal state times some function. And outside of the superconducting states, this is equal to 0. We don't have any superconductivity, so it is just like that. Okay? So this is two results which we got. So in the superconducting states below critical temperature, I'm having this, and above the critical temperature, I would have just the normal Fermi energy, normal fermions. So now if you take the difference of those two things, below the critical temperature and above the critical temperature, which is here, I'm exactly comparing those two results. Then the difference of those two expressions, if you just look, you are getting just that. But now you recognize that, okay, this is nothing else as the Cn of the normal temperature. So you are sitting this fantastic prediction of the BCS theory, which is confirmed that the change of the heat capacity divided by the normal state heat capacity, which is superconducting capacity minus normal heat capacity divided by Cn, is a universal function. It's a universal number. And it's just this 12 divided by 7, some zeta function of 3, and it's some number 1.43. So this jump, relative this jump, is 4.3. And this was observed in aluminium and other nice simple metals. And this was the super triumph of the BCS theory, that they are able to get this number. Okay, so this is again something fantastic of that, and it's hidden there. So I'm just showing you that, okay, there are calculations how to get it, and I just want to show you a few such calculations, how to go over that. So you just use everything what you know, and on some places then you need to use the mathematics, and this mathematics can be sometimes heavy, because you get some integrals of the special functions, but people before us, they were quite clever and they know the answers. And okay, so this is what we are getting. So you see that calculation is principle simple. You start from the definition and you go, and whenever you can, you simplify it. So that's what I wanted to say. So we see that from the BCS theory, we are exactly getting this jump. Okay, which is great. Good. So I will finish here. I will upload again the notes. They're not super good. I still need to improve, add some figures or things like that. But I think in the next generation they will have super notes. But you are the first one which I'm teaching that. So I am still expanding and making it better and better. But was it clear how I did the calculation? Okay, so next time I will start to do, I will upload, and it would be homework probably, in the else of notes are already on in the Moodle. So you will need to read the final chapter in that, when he derived the current. We can also derive the current, superconducting current from that. And I will leave that for you as a reading. And next week I will start with the Josephson equation. So I am finishing the phenomenology, microscopical and phenomenological superconductivity, and now we will go to the junction physics. And there was the other famous guys who was Brian Josephson, and Brian Josephson discovered Josephson equations, and they are describing the Josephson junctions. And Josephson junctions, people can play with them up to infinity, and there were, many interesting physics with the Josephson junction, so we will try to understand the physics of that. And it's again some phenomenology at the end. Microscopically, it would be kind of the BCS theory, but we would like to get some equations which we are able to play with, like the London equations or the Ginzburg-Landau equations. And in the case of the junctions, this is the Josephson equations. So this will be the next time, okay? But maybe I will also make some homework sheet such that I can get some time and you calculate something on the blackboard. So maybe over weekend I will submit some problems, and then I hope that you will be able until Thursday to solve a few problems. Okay? Perfect. That's it. Thank you. Okay. Maybe you will help me to switch it off. Check in. Thank you.